In this lecture, we are going to learn very important idea called the Taylor and Maclaurin series. So it's called Taylor and Maclaurin. Taylor and Maclaurin series. And you can see that the Maclaurin series is a special case of the Taylor series, but it still has a new name. So this is the short version. So we're going to discuss like only the important topics here. So this is very important. The one of the ideas is very important because this is like pretty much everywhere. So you can see this is in physics, engineering, applications, computer science, and everywhere. So let's look at the idea, like what's really going on here. So let's suppose you have so we can assume a function is equals to a series and going from 0 to infinity with some coefficient x minus a to the n. So we assume that there's a the function is equal to a power series. So if you expand this looks like c0 and then c1 x minus a and then c2 x minus a squared, c3 x minus a cube, like that. Okay, so what we're gonna do, let's plug in x equal a. Okay, so this is, you know that this is about a, right? About a. So you have a series near a. Near a means, you know, in a certain interval. So that's the interval I. Okay, so that's what called near a. This interval may be everything, but we don't know that. Okay, so let's plug in a. So if you substitute a, what happened? So let's say at x equal a, it is f a. If you plug in a, what's going to happen? c0 plus, you see when you plug in a, this is going to be 0. The second term, third term, 0. So all those terms going to be 0 except the first one. So this says that c0 is simply equals to fa. Okay, so c0 equal to fa. So we know the first coefficient. Now what we're going to do, we're going to take the derivative and plug in a again. So let's take the derivative first. So if you take the derivative, so take the derivative of the original series, or the f prime x equals, if you take the derivative, what will happen? c0 is a constant, so you get 0. And the first second one says that you get c1 because derivative of x minus a is 1, plus from the second term you're going to get 2 times c2 x minus a plus 3 c3 x minus a squared, like that. Now what we're going to do, we're going to plug in a. So at x equal a, as before, f prime a. So what's going to happen? You're going to get c1 plus, you see when you plug in a, this gets 0, so everything else is going to be 0. So that means this is going to give you c1. So what is c1 equals to? F prime a. So that is c1. So we know c0, c1. Okay, so let's keep doing it. Let's take this next derivative. If you take the second derivative, you're going to get 2c2 plus 3 times 2 times c3 x minus a, and in the from this next term you're going to get 4 times 3 times c4 x minus a squared, like that, because you take the derivative twice, so you need to multiply the power by 2 times. Okay, and then as before, f double prime a is equal to 2 times c2, everything else 0. It's going to give you c2 as f double prime a divided by 2. Okay, divided by 2. So keep doing. So what's going to happen in the next one? So if you take the third derivative, then what's going to happen? 3 times 2 times 1 now, C3, plus from the next one you're going to get 4 times 3 times 2, C4 x minus a, like that. And again, when you plug in a, except the first term, everything else get cancelled. Okay, so this says that C3 equal f third derivative evaluated at a divided by 3 to 1, that means 3 factorial. So that the factorial term is there. For example, the previous one you can write as f second derivative a, the 2 factorial. And this one you can write as f first derivative divided by 1 factorial. So the first one you can write as f a divided by 0 factorial. 0 factorial equals to 1. That we know, that's a convention. Okay, so that means you're going to see, if you look at the third one, you can see that there's a pattern here. So what's the pattern? You can write the nth derivative. So the nth derivative looks like, so nth coefficient look like Cn equals to the nth derivative evaluated at a divided by factorial n. So that is the general coefficient. So once you put those coefficients, you're going to get what we call the Taylor series. Okay, so it's a very simple idea. So this is the only one you need to remember, the format of the coefficient. Everything else is pretty clear. So let's continue that. So we can have the definition, Taylor series. So Taylor, and we can talk about both the Maclaurin series. Maclaurin series. Taylor and Maclaurin series. So the definition is, let f be a function, with, we can say, derivatives of all order, because we need to continually take the derivatives. So let f be a function with derivatives of all orders, derivatives of all orders, derivatives of all orders in an interval containing a, in an interval containing a. So you're gonna find, so there's a here. So you should be able to do that in an interval containing a. So it may be like that. It can be like weird like this also, but we can handle that later. But a, that's the interval. So it should contain a. Okay. So then the Taylor series. Then the Taylor series. Then the Taylor series. Taylor series of f at x equal a is given by, so we can write this as a sigma notation. So we can write this as a sigma. Let's use index. I'm going to use k here, but you can use any index. So k going from 0 to infinity, the kth derivative evaluated at a, factorial k x minus a to the kth power. So you can see that the k you can find in 3 places, actually 4 places. The first outside, and then you have k up there, down, and there. So there are 4 places. Okay, and then if you expand this, let's expand. Just like first few terms, just to see the pattern. So if you plug in k equals 0, what will happen? 0 derivative is the function itself. K's 0's factorial means 1. x minus a to the 0 power is 1. So you simply get fa, the first term. What's the second term? The first derivative evaluated at a divided by factorial 1, which is 1, and then x minus a. If you write the next term, it is the second derivative evaluated at a divided by factorial 2 x minus a squared, like that. So if you write the general term, it's going to be look like f to the kth derivative evaluated at a divided by factorial k x minus a to the kth power, and then we can repeat the pattern. So this is what we call the Taylor series of the function f. But there's a special case. What's the special case? When a equals 0, okay, that's a very special case. When a equals 0, it is called the same thing. Okay, it is called the Maclaurin series. It is called the Maclaurin. It is called the Maclaurin series. It is interesting actually. Maclaurin series came after the Taylor series. So this is a like very rare situation. Okay, and is given by so let's write it again. What we need to do, just put a equals 0. That's it. It's given by sigma k going from 0 to infinity f to the kth derivative evaluated at 0 now. K factorial. This is x to the k. That's it. So it is f to the 0. F prime 0 factorial 1, we don't write it, but that's okay, just for the pattern x, and then f double prime evaluated at 0 2 factorial x squared, like that. So that's what we call the Maclaurin series. Just x go a 0. Good. So now what we need to do, let's do like some examples. So there we had two formulas, one for the Taylor series, equation number 1, 2 for the Maclaurin series. Okay, so the Maclaurin series and the Taylor series. So the Maclaurin series is just a special case of the Taylor series when a equals 0. When a equals 0. So you don't want to remember any new formula here. Just remember one. Okay, so let's do maybe 2 examples. Just to understand how to do it. So we can start with something easy. So let's do this one. So the first example, find the Maclaurin series, because that's easy. Find the Maclaurin series. Find the Maclaurin series of fx equal e to the x, and find where it converges. Find where it converges. Okay, so let's try to do both. So let's find out Maclaurin series. Okay, so Maclaurin series means, so let's go for the answer. So the answer is a Maclaurin series, so that means a equals 0. This is the function ex, or fx equal ex. One of the interesting property of ex is all the derivatives are equals to 1. So if you take the nth derivative, this is equals to ex. Okay, so at 0, so nth derivative at 0 implies 0, e to the 0, which is 1. So that means all the coefficients are 1 for all n. For any n, the coefficient is simply 1. So that means your Maclaurin series. So the Maclaurin series or the Taylor series at a equals 0. Maclaurin series is simply sigma. We can use the index n for this one because this is very common. but normally we use k. So n going from 0 to infinity, x to the nth derivative evaluated at 0 over n factorial x to the n. So let's plug in. So that means what happened, since all the derivatives are 1, you can rewrite this one, put in the 1 for the derivative. It is simply xn over factorial n. So that is the series. If you look at few terms, if you plug in n equals 0, what do you get? X to the 0 is 1, factorial is 1, so it's 1. The next term, x to the 1 over factorial 1, x to the 2 over factorial 2, x to the 3 over factorial 3. So that's where it's coming from. We have seen this one, but this is where it's coming from. Okay, so it's very easy. So we're done with that part. Let's see guys converge. For the convergence, we can use a ratio test. Okay, so here a at the nth term is simply xn over factorial n. Okay, so then by the ratio test, okay, we use the ratio test. What we do, we're going to look at the ratio. So it is, what do you get? N plus 1. So it's x to the n plus 1 over n plus 1 factorial. Make it upside down and divide, upside down and multiply, because the division fraction. So upside down multiplies a factorial n of x to the n. You can see this calculation. We know this calculation now. N plus 1, you can expand n plus 1 times factorial, so get cancelled. Xn get cancelled, so you simply end up getting x over n plus 1. That's it. So you know that this goes to 0, which is less than 1, as n goes to infinity. So that means it's converge for all x. So by the ratio test, we know that the converges for all x. Why? It's 0. So that means whatever x you put is converge. Okay, so it converges for all x. So because of that, then we can simply write ex, because converge, whatever value is going to converge. So we can write as ex as simply sigma n going from 0 to infinity x n of n factorial, because it converges everywhere. So this is simply 1 plus x squared over 2 factorial plus x 3 over 3 factorial, like that, for all x. Okay, all x. Okay, so this is an interesting formula, and you need to remember this identity. So we're gonna make it an important formula. Okay, so this is very important formula. Interesting part is it converges for any x. It converges for any x. Good. So let's try to do a slightly different example. Now let's try to find a Taylor series. So this is a Maclaurin series. This is an easy one because at 0. So let's try to do a Taylor series at a different point now. So the next example, let's say find the Taylor series. Find the Taylor series of fx 1 of x at let's say just pick something easy like a equal to, and also where does it converge, where does it converge to 1 of x. So we know that it is not always equals to 1 of x, because there is a interval where it's going to converge. So let's try to find that. Okay, so let's try to finish the problem. So it's very similar to what we did before. So what we need is, we need a derivative evaluated at 2. That's it. Okay. So so we're gonna say we need derivatives. We need derivatives evaluated at a equal 2. Okay. So let's do it. So we know that the function fx is, you can write as x to the negative 1, because that makes it easy. Now we're going to find the derivative. So f prime x is simply negative x negative 2. Second derivative is negative times negative 2 means 2 times x to the negative 3. So so keep doing it. So what will happen, every time you introduce one more number there, and also with the negative sign. So that means if you look at the general term, looks like if nth derivative x is equals to negative 1 to the nth, because you take n many derivatives, and also every time you introduce a number. So that means if you do n times, you're going to go n factorial. So that's what you get, times x to the what do you get, x to the negative n plus 1. So that means you can write this on x to the n plus 1, because when you take the derivative of a negative power, it always increase by 1. So if you do n many derivatives, it increase by n. So we can write it like that. So that is what a general term looks like. This is what a general term looks like, because if you want to write the actual final series, you need the general term. Okay, so I hope that's clear. So let's try the Taylor series. So it is tx. You can write tx for Taylor series. So let's try the formula. K going from 0 to infinity. F kth power evaluated at 2. K factorial. X minus a to the k. So let's plug in. Start with k equals 0 as before. It is f2 plus f prime 2 x minus 2 plus f double prime 2 factorial x minus 2. So those are the first few terms. So let's plug in. So if you plug in, what do you get? What is f2? F2 is what we're going to do is we want to evaluate those derivatives at 2. So if you plug in 2, so you get 1/2, and then minus f prime 2, go to the prime and plug in 2, so it is negative 1/4. So right, negative 1/4. So you can write this one as x minus 2 to the 4th. So and then plus, because it's sign change, plus minus, it is x minus 2 to the squared, and then what's going to happen, there's a 2 here. So for the second derivative, so you're going to get x to the you can see that x to the because x equal 2, so when you plug in 2, this goes to x to the cube. So that means 2 over 2 cube. So it is, and then also there's a factorial. The factorial 2 cancel the 2 here. So actually I can write everything. So here you have factorial 2, and your derivative is 2 over 2 to the cube, right? So like that. So you can see that this and that gets cancelled. So so if you write the general term, what's the general term looks like? So let's write the general term. So general term is, we have negative 1 to the nth power, and then you have factorial in, get cancelled. So you're going to get x minus a to the you have n divided by 2 to the n plus 1, because the factorial get cancelled like that. So that is the general term. Okay, so so you can write few terms like that. So that is the Taylor series for that. So if you want, you can write this in a sigma form. So sigma, so we can say k going from 0 to infinity, -1 to the nth power, x minus a to the, not n, we say use k here. So whatever the same notation, you can use that. Yeah. So we have n power, this is 2 to the n plus 1. Okay. Yeah, so now what we need to do is we need to know where this is going to converge. So if you want to know where this is going to converge, so what we try to do, we can use the ratio test. So so what you need to do, actually you can see that this is in this case this is a geometric series actually, because if you pull out if you think of the n term, you can see that this is geometric series. So this is a geometric series, so you can use a ratio test, no problem with that, but they have a shortcut. So this is a geometric series. It's a geometric series R. What is the R here? So R is the terms with the n. So R equal in this case a negative x minus a over 2 without n, because we have 2 n plus 1, that n plus 1 means 1/2, so you can pull the 1/2 out. So if you consider only the n terms, so these are the n terms, this one has n, this one has n, this one has n. Consider only the one with n, the plus 1 you can pull it out. So that means that's why you get negative x minus a, one of them, and 2. So and then this says that we can take the absolute value of that, and then we're going to make it less than 1. So in this case actually a is, yeah, I put a, it should be a equal has to be 2. So this is 2, yeah, so this is 2, and also in this formula this is 2. So this has to be 2. This is 2 and this is 2. Okay, so and this is 2 as well. Good. So so what's gonna happen now? So this says that x minus 2 is less than 2. So that means if you draw it, so you start with 2, go 2 to the two sides. That's why I said the radius is 2. That's the radius, it is 2. So go to the two sides, that means it's going to be a 4 and a 2, 4 and a 0. So that's where it's going to converge. And then you can consider the corners as well, just to find the actual interval. But we know that for sure this is going to converge here because of the geometric series. But this is geometric series, that means that's the only one is going to converge. So the interval of convergence is only going from 0 to 4. So that's where it's going to converge. Okay, because the reason is this is geometric series. Geometric series only converge when R is less than 1. Okay, now we can notice one more thing. So let's see whether this can actually converge. Okay, so so what's gonna happen now? We can find the actual sum of the series. So since this is geometric series, the sum of the series, sum of the series is a over 1 minus r, that we know. So a, what is a? What is the first term? The first term is 1/2. See, so we're going to plug in that. So that's the first term, 1/2, and then 1 minus. So what is r? R is negative x minus 2 over 2. That is r. So if you simplify, what do you get? So it is 1/2 1 plus x minus 2 over 2. If you divide the top and bottom by 2, you're going to get 1 over 2 plus x minus 2, which is 1 over x, as we expected. So that means if you consider all the terms, if you go to infinity, you see that the series exactly converges to 1 of x. Perfect. Okay, good. So that's the important. That means that series is going to converge to that function, whatever the function that we have. So let's extend this idea. So so what we're going to do, we have a special case. So what we're going to do, we're going to truncate the function at the nth place. So you're going to consider only the first n terms. If you consider only the first n terms, you're going to get what we call the Taylor polynomial. So that's like kind of new, just a new term, but it's just a special case, a truncation of that. So the Taylor polynomial, Taylor polynomial, Taylor polynomial of degree n, Taylor polynomial degree n. So let's write it. So what we have, the nth degree Taylor polynomial, Taylor polynomial, nth degree Taylor polynomial, nth degree Taylor polynomial is given by what we're gonna do, we're gonna call it Tn. So that's what we call it, Tn. Tnx is a polynomial. What we're gonna do, we're gonna sum it only to n. So this is the reason why we use k here, because you have to put n there. Okay, when you put n, it's called the nth degree Taylor polynomial. So it is f k evaluated at a. It's the same thing, but it stop at n. That's the only difference. Factorial k x minus a to the kth power. So that's nothing, no different. So that's what we call the nth degree Taylor polynomial. So if you write a few terms, it's the same thing. You only stop at nth degree term. So f prime a divided by factorial a x minus a, and then f double prime a divided by 2 factorial x minus a squared, like that. So you're going to stop at nth derivative. So it's f nth derivative evaluated at a divided by n factorial x minus a to the nth power. So you're going to get a this. So you can see that this is a nth degree polynomial. It's a polynomial in x. Okay, so you can see that because of that last term, so this is simply going to be the whole thing going to be nth degree polynomial in x. Okay, that's the reason why we call it n degree polynomial. But as a formula, you only go up to the nth term. So this is like kind of common thing that we do, because this approximation, this is going to give you nth approximation. So for example, so let's say if you have a line, remember we called about the tangent line. So that is the first degree Taylor polynomial, the tangent. So we have the tangent, so that is the first, so first degree Taylor polynomial. Okay, first degree, first degree Taylor polynomial, Taylor polynomial. So that means what is that actually? Tx, so T1x, this is simply fa plus f prime a x minus a. So that's the first degree Taylor polynomial. That is the line. Okay, the equation of tangent line. So this is the equation of the tangent line. So the equation of the tangent line, equation of the tangent line. So that's something we know, but that's the first degree Taylor polynomial. What we can do is we can go nth degree, so we're going to get better and better and better. So what we get when you go more and more, it get closer and closer to the graph. So for example, if you have the second degree, it's going to go like that, like this. See, so it's better. That's the second degree. That's the first one. Okay, that's the first degree. So because when you increase the degree, it's going to get closer to the actual curve. So that's the actual curve. So I hope you get the idea. Okay, so let's try to look at a few things. For example, so we can write this one. So another example, for fx equal ex, that's easy one. Few, we can say Taylor polynomials are few Taylor polynomials are, so the t1x is the first degree polynomial, that is 1 plus x, we only consider up to degree 1. T2x means you're going to consider up to degree 2, that is x squared or factorial 2, and then T3 is you're going to consider up to third degree, so 1 plus x squared over 2 plus x3 over 6. So that's the third degree Taylor polynomial. You can see that when you graph it, they get closer and closer and closer. So more the better, So let's try to do a actual problem here. So let's try to find a Taylor polynomial of degree maybe 3 of a certain function. So let's do this one. So find the third degree Taylor polynomial, and Taylor series, and the Taylor series of fx equal ex at a equal 2. So let's try to find at a different point. So problem is not that difficult, it's the same thing. What you want to do, you evaluate at a different point. That's it. Okay, so the answer, we know that fx equal ex, so all the derivatives are ex. So that means if you evaluate this at 2, it is e to the 2, just e to the 2. Then we can write the Taylor polynomial tx, which is sigma n going from 0 to infinity f n 2 n factorial x minus 2 to the n. So if you plug in here, so you get sigma n going from 0 to infinity e squared over n factorial. We know that the derivative is e squared, so we just plug in here. Okay, that's where it's coming from. So this x minus 2 to the n. So if you want, you can pull that e squared out because that's a constant. So then you're going to get sigma n going from 0 to infinity x minus 2 to the nth power divided by factorial. And we know that this is going to converge everywhere. That's part of the exponential function. A result of exponential function is going to converge everywhere. Okay, so that's a complete series. But if you need the third degree polynomial, so that means we're going to stop at 3. So the third degree polynomial, third degree polynomial is, so let's write only up to the degree 3. So that means sigma n going from 0 to 3. Okay, f n 2 over n factorial x minus 2 to the n. We don't want to do everything again because we already did that, but I'm just going to write the only up to the first, only up to degree 3. So let's write, so that means it is e squared, the first term, when you plug in 0, and then you're going to get e squared x minus 2, and then you're going to get e squared x minus 2 squared, and the last one is e squared x minus 2 cube over 6. Okay, so that's the third degree Taylor polynomial of ex at a equal 2. Okay, so it's not that difficult. So this is like kind of common thing that you need to know. And also let's try to talk about a little bit more. The question is, we know that like when you truncate at the nth degree polynomial, you ignore a lot of terms. Those terms gonna create an error. Is that right? So there's an error when you truncate. So let's discuss that. So the error for nth degree polynomial, nth degree Taylor polynomial. So we normally call this error is Rn, nth error. The error is the difference between fx and the corresponding Taylor polynomial. So we normally take the absolute value. So that's the error. So we take the difference, but you can actually take the absolute value of that just to find the actual number if you want. But this is the error. Error is the difference between the actual function and the corresponding Taylor expansion of degree n. So and then if we do that, then what we can do is we can write, this says that fx, if you move to the other side, it is tnx plus rnx. You can write the Taylor polynomial plus the error term. So what it says that in theory it says that the error is bounded by a certain number. So what it says that this error, whatever the error we have, is bounded by m over n plus 1. That's the next term of the Taylor series, the next term, to the x minus a absolute value n plus 1. It's always bounded by that for what a has to be in that interval of convergence. Okay, so where is r is positive, you know that. So this error is bounded by that, and where this m is an upper bound, such that the derivative, the next derivative plus first derivative, is bounded by that m for the same range. So that's what's going to happen. So you can see that this error is bounded by this particular number, So if that means if the derivative is bounded, completely bounded, that doesn't happen for certain functions. Okay, so it's completely bounded, what's going to happen? This error goes to 0. Error goes to 0 means it's going to converge. So we can write this one, if the limit of the error, term Rn equals 0, then what's going to happen? Then we can write as fx equals simply the Taylor series. So fn a over n factorial x minus a to the n. So we can write it like that if the error is 0. Okay, that means it's going to converge. So converge, we write it like that. So that's the kind of theory. So this happened on some interval about a. Yeah, good. So that's the kind of major things. So we're done with the major things, but I would like to do maybe like just a few more examples just to kind of see what's out there. So let's do so we have already done with all the major topics of this one, but let's do just a few more examples. So more examples. Okay, just more examples. So let's do this one. Let's try to find the Maclaurin series of sin x. So find the Maclaurin series, series of fx equals sin x. So if Maclaurin series means a equals 0, so so that means we know that a equals 0. So what we're going to do is we start with fx, so which is sin x, evaluated at 0. This is Maclaurin series. So it is sin 0, which is 0, and then take the derivative. which is cosine x evaluated at 0. So it is cosine 0, which is 1, f second derivative, that is negative sine x evaluated at 0, which is 0 because sine, and then take the third derivative. We do that until we see a pattern. So it's negative cosine x, so it is f third derivative evaluated at 0, so it is negative cosine 0, which is negative 1, and then fourth derivative, so we use 4 here. So you can use the Roman numbers after that. You have to use the Indian Arabic here, but that's a kind of a common thing that we do. Otherwise, get like looks like ugly. You know, like for example, if you want to go 8th derivative, it's really long, so we don't do that. So minus. Now what's going to happen when you take the derivative of the next term? It is minus cosine means negative sign, so it becomes sine. That means it's going to come back to the original one. So that means it's going to create a cycle. So right. So it's going to create a cycle. It's going to go in that pattern. So once you see a pattern, it's easy. So we kind of do it until we see a pattern, then we can write the general term. So so what's going to happen here? Now if the fourth derivative evaluated at 0 is 0. Okay, so that means you're going to see only odd numbers. You see that? It's only for odd n. Okay, only for odd n we're going to see non-zero, but for all even powers we're going to see 0. Okay, only for odd powers, see 1 and 3 we're going to see that. So that means you get a 5, you're going to get 1, 7, you're going to get negative 1. So that's what you get. Okay, so that means so what we notice is, so we can write the what we see actually. So we see that if 1 is 1, if 3 is negative 1, and then it's going to repeat. So if 5 is 1, if 7 is negative 1, like that. So only the odd powers, everything else is 0. So let's now go back and plug in. So if you go and plug in, what do you get? So this is a Maclaurin series. Is m x is, we see that if I'm going to write all the terms, just few terms, just to practice. So it's x, and then f double prime 0, 2 factorial x squared, f triple prime 0, 3 factorial x3, like that. But what happen is all the odd powers, all the even powers got cancelled. So this is gone, this is gone, like that. So what you only end up getting is the odd powers, and also sign change. So what we get is, we can see that we get the first term is x, because f prime 0 is 1, and then the third one is negative 1, so it is x3 over factorial 3. Next coefficient is 1, so it is x5 over factorial 5, and the next one is again a negative, so like that. So that means you can see that only the odd powers are there. So that means if you want to write this as a general formula, so sigma n going from 0 to infinity, that's a sign change. So that means a negative 1, some kind of power. We're going to put the power later. So we need the odd numbers. Odd numbers means we can write x2 n plus 1. So you want to make sure that you get x. When you plug x equals 0, yes, you get x. And then divided by 2n plus 1 factorial. So now we know that when you plug in n equals 0, you should get a positive sign. That means this has to be n then, right? So that is the formula. Okay, that's a formula. And then we can see that by the ratio test. I'm not going to do it, I just say it. By the ratio test, you can see that the converges everywhere. Converges everywhere, because you can see that the limit goes to 0. every term is for all. Okay, for all. So that means because of that, we can write this result finally like that. So this is something that we need to remember. So sin x is the sigma n going from 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So if you write first few terms, it is x3 over factorial 3, x5 over factorial 5, and minus like that. Only the odd powers start with x. So and true for all x. Okay, so we're gonna put this in a box. It's important formula. So you can see that this is like very close to the exponential function, but you only get the odd terms with the sign change. Okay, so this is like for all x. So you can see that one of the consequences is that when x is close to 0, you can ignore all the largest powers. Then it says that sin x is very close to x. So this is one of the thing that we use in physics and other classes. So this is where it's coming from. You can see when x is small, all those large terms you can ignore, so you only get the first term. Okay, this is where it's coming from. Okay, so so that's about that. And then so let's do maybe one more. How to do for example find the Maclaurin series for cosine. How about a question like that? So the next one, find the Maclaurin series for cosine x. Now what we have a shortcut actually. We don't want to go the long way because we know that the cosine is the derivative of sine. So note that the cosine x is the derivative of the sine x. So what we're gonna do, we're gonna plug in here. So it's a d by dx. We're gonna put the series here. So sigma n going from 0 to infinity. We're gonna plug in it here. 2x, so x to the 2n plus 1 over 2n plus 1. Switch the sigma and the summation. So if you take the summation out and take the derivative of the inside function, so what's gonna happen is, what do you get? So derivative is 2n plus 1 x to the 2n. Bottom I'm gonna expand. I'm gonna write the, okay, there's a factorial here. I'm gonna write that one. I'm gonna expand one of the terms and then leave the rest in the factorial form. So what's gonna happen now, you can see this get cancelled. Now you only end up with even powers because of this argument. So what's gonna happen, you only end up with the even powers. It's very similar, but the even powers. No change to the sign term. So you get x2n over 2n factorial. Only even powers. Last time only odd powers. This time it's only even powers. Okay, so so we can even expand it. So expand and see what we get. So let's write this as a final formula. So what's gonna happen? So we have cosine x, which is equal to sigma n going from 0 to infinity, is very similar to what we had. Oops. So this is n. So it's very similar to what we have, but we have x to the 2 and only the even powers over 2n factorial. What is the first term? If you plug in n equals 0, what do you get? If you plug n equals 0, you get 1. Where all the terms are 1. So you get 1 minus, when you play n equal 1, you get minus x squared over 2 factorial. So you can say 2 factorial is okay, plus, just for the pattern, x4 over 4 factorial minus x6 over 6 factorial, like that. Okay, again, this is also true for all x. So this is another formula. So all the even powers now, all the even powers, didn't go well. So good. So we get all the even powers. Good. So again, for all x. So this is for all x. It's true for all x. That's one of the benefits of this one. And also you can see that when x is very close to 0, you can ignore all the higher powers. Then you can see that when x is close to 0, cosine x almost close to 1. So we use this result in optics and other places. So this is where it's coming from. Cosine x equals to 1, because we can ignore all the other terms. Okay, so there are certain functions. So I'm gonna do like maybe like just let's do like more examples. So how about this one? So are you gonna say more applications? More applications. More applications. More applications. So let's say something like this. So what you can do is you can multiply and divide Taylor series on the interval of convergence. Okay, so we can. So I'm gonna write it. Yeah, let's write that first. So so we can say. So we can multiply, divide, add, subtract, Taylor or Maclaurin. When you say Taylor, it's already included Maclaurin, Taylor series. So we can do that. So we can multiply like 2 together. Okay. So let's do one example like that. These are just extra examples. Okay. So so let's say find the Maclaurin series of find the Maclaurin series of let's say x cube cosine x. So you can see that this is not much hard. So what we're gonna do, we're gonna start with, so the answer, we already know what's the cosine series. So we say x3 cosine x is equal to x3 times cosine. We're gonna plug in the series that we have. So if you need the general one, we can sub in sigma, but if you just need a few terms, then you can go with the approximation, just write first few terms. But if you need a general one, we can write the general one. So it is x to the 2n over 2n factorial. Now what's gonna happen, so when you bring x3 inside, just add extra 3 to the n power. So that means we're gonna get sigma n going from 0 to infinity, negative 1 to the n power x 2n plus 3 over, there's no change in the bottom. So that's the Taylor series for x3 cosine x. Okay, so we can do similar things, even like, you know, we can do like little harder one if you want. So this is a extra problem if you want to try. What about 3x cosine 3x cosine, let's put something here, x squared over 4, something like that. So what you want to do, go to the cosine series and first plug in wherever you see x, plug in that. Then you're gonna get the cosine x squared over 4. Just go to the cosine series and plug in, just replace x by x squared over 4, and then you're going to multiply by 3x after that. Just multiply by 3x and then simplify, bring everything inside 1, then you're going to get the expansion. So you can try this one for an extra credit problem. Okay, good. So for the previous one, if you want to write just few extra terms here, so what are the first few terms? If you want to write first few terms, what are you going to get? You're going to get x3, the first term, and then you're going to get x5 over factorial 2 plus x7 over factorial 4, and then minus x9 over factorial 6, like that. Okay, those are just few extra terms if you need, just few terms. So, and how about this one? I'm going to give you like another problem like this. So this also you can try. So let's say you want to find sine x times cosine x squared over 3. So now what we are going to do in this case, you're going to substitute for both series, just maybe multiply first few terms, like write the first 3 terms of the first both and then multiply them together. Okay, so write first few terms of both series and multiply together. Write first few terms, maybe like first 3 terms of each series, just to get the idea. Okay, so you can try that. So what I'm going to do next is I'm going to give you a common table of series, common table of Maclaurin series. So these are some of the common series that we derived in this and the earlier section. For example, the first one is the geometric series, and the second one is the exponential function, and then we have the sine function, cosine function, tan x, tan inverse x, we derived that in the previous discussion. Log 1 plus x, we derived that in the previous discussion as well. The last one is what we call the binomial theorem. So so this is like something like really interesting. So this is what we call the binomial theorem. So I'm going to write it. It's called the binomial theorem. Binomial theorem. And so k to the kn is what we call the binomial coefficient. Binomial coefficient. Binomial coefficient. This is something that you learn in discrete mathematics. So the first few binomial coefficients are given here. So yeah, so these are like kind of good ones to remember if you can. But some of them, you know, we're gonna give you in the exam, in the, you know, maybe as a like, you know, attachment. Good. So let's do maybe one last problem using these ideas. So how about this one? So this is the next problem. This is the last problem. So we can do actually really amazing things. So this is one such situation. So we can even use this to find like a limit. So evaluate the limit of x goes to 0, ex minus 1 minus x over x squared using this Taylor series. So but we know that we can do this in a different way. One way to do this is you can use the L'Hopital's rule here, because you can see that when you plug x equals 0, the top and bottom is 0, so you can use the L'Hopital's rule. That's one way to do it. But here what we can do, we can use the Taylor series. So we're gonna substitute. That's what we do. So we're gonna have x goes to 0. So we have ex minus 1 minus x over x squared. So this is the limit. X goes to 0. So what we can do, we can write first few terms, not all, like first few terms. It's a ex. Ex is what? 1 plus x plus x squared over factorial 2 plus x3 over factorial 3, maybe like about 4 terms. That's enough. And then the rest, minus 1 minus x divided by x squared. So we're going to simplify this. You can see some of the terms get cancelled, so this cancels with that, and then this one cancels with that one. Okay, so those two get cancelled. So that means you simply end up getting the limit. So this is the limit of when x goes to 0. So you end up getting only x squared over 2 factorial plus x3 over 3 factorial, and then I can write one more, x4 4 factorial, like that, divided by x squared. That means we can divide by x squared now. So if you divide by x squared, what's you're gonna get? You're gonna get the limit x goes to 0. You can see that you only end up getting 1/2, and then x over 3 factorial, x squared over 4 factorial, like that. But you can see when x goes to 0, all those terms goes to 0. So this goes to 0, this goes to 0. So that means you simply end up getting 1/2. So this is another way to find limits using Taylor series approximations. So we simply substitute for ex just using a few terms. So that is the approximation of ex. So I'm going to give you a challenging problem. If you can try this one, this is a little difficult. Okay, so you might even need to divide two Taylor series. Again, just consider first few terms and then divide. So that's what we normally do. So let's say find an approximation to 0 1 sine x cosine x over 2 divided by ex dx. Okay, so this is challenge. Okay, so this is the end of the short version of the Taylor series discussions.